Hello everyone, my name is Hamid Tabani from NavInfo Europe Advanced Research Lab here in Eindhoven, Netherlands, and I'm glad to present our accepted work entitled Improving the Efficiency of Transformers for Resource-Constrained Devices. This paper has been accepted in the 24th Euromicro Conference on Digital System Design, DSD, and has been conducted in collaboration with my other colleagues, and I'm glad to present the paper and the results that we got from our work. In this work, we are focusing on transformers, which are newly introduced form of architectures, deep learning models, which are mainly based on self-attention mechanism. Transformers are now very common and they are used in a variety of domains such as natural language processing and also computer vision like detection, segmentation, classification, and they show that they can be really powerful and provide significantly better results compared to previously developed models and former architectures. The main motivation to use the transformers is basically the fact that transformers are providing lots of benefits and they can be also beneficial when they used on embedded and edge devices and not only the very high-end and powerful processors and GPUs. But we are certainly observing lots of limitations to use transformers on resource-constrained devices. The main limitations are the limited memory capacity, the limited computation resources on these kind of devices, the limited power and also energy resources, and limitations with having memory bandwidth. With these factors, deploying and using transformers on low power, embedded and edge devices are become almost impossible or sometimes very limited. In this work, we are focusing on analyzing the transformers when we're performing inference on them, identifying key functions which are the most time and energy consuming when deploying the transformers, and also we propose to apply clustering schemes on two of the state-of-the-art transformer models for computer vision classification, and we show that we can reduce the overall size of the parameters and also directly impact the memory bandwidth. We will show that significant energy and performance improvements can be achieved with negligible impact on the accuracy of the models. We present the existing trade-offs and opportunities to maximize the utilization of specified and specialized accelerators for these kind of workloads. After the introduction, motivation and contributions that has been discussed, I will continue this presentation by providing a background on transformers and their architectural design and their benefits. I will then continue by providing performance analysis of two of the main transformers on the computer vision classification tasks, which are state-of-the-art transformers, and then I will focus on our proposed optimizations and the clustering techniques. Then I will introduce our methodology, the results that we obtained and how we can interpret those results, and finally I will conclude the presentation. The transformers are proposed and developed in order to solve the issues with the former designs like the RNNs and LSTMs. Basically, the issue that affects RNNs is also affected LSTMs when sequences are too long and they both perform very poorly. The explanation for this is that the likelihood of remembering the meaning of a word far away from the actual word which is being processed decreases exponentially with time. As a consequence, when sentences are long, the model often forgets the content of positions further down the sequence. Another issue with RNNs and LSTMs is that they are difficult to parallelize for processing sentences since they must be processed word by word. Furthermore, there is no paradigm for long and short-term dependencies. So in summary, LSTMs and RNNs have main issues which are as follows. First, parallelization is hampered by sequential computation. Second, long and short-term dependencies are not explicitly modeled. And three, the distance between positions is a straight line. So when attention mechanisms were applied to RNNs, they start to result significantly better and the performance improved a lot. The transformers introduction revealed that attention mechanisms were affected in and of themselves and that sequential recurrent data processing was not needed to achieve the performance gains of RNNs with attention. The transformer, instead of being an RNN, actually uses an attention system that processes all tokens at the same time and calculates attention weights between them. Transformers can be trained more efficiently and more effectively on larger data sets because they do not rely on sequential processing and lend themselves easily for parallelization. So as an example, Vision Transformer is the name of the overall architecture, like what you see here, which is called VIT. It first creates patches from a picture and gets the patches as flat as possible. Then it converts the flattened patches into lower dimensional linear embeddings. And next, positional embeddings should be added to the sequence and be fed as an input to the standard transformer encoder. Image labels are used to pre-train the model in a fully supervised manner using a huge dataset. Finally, image detection should be fine-tuned on the downstream dataset. We show here that vision transformers like this one, VIT, are a straightforward application of the transformer architecture in image classification domain. As discussed earlier, in this work we are focusing on vision transformers, and in this work we are using two of the state-of-the-art vision transformers for classification. The first is called DIT, which is Data Efficient Image Transformer from Facebook, and the second VIT, or Classification Transformer from Google. The first analysis that we have done was the execution time breakdown for both of the models. As it shows, we have observed that across different operations, matrix multiplication is the dominant operation for both of the models, in which the DIT spends more than 55% of the execution time doing the matrix multiplication, and also the VIT more than 60%. Our analysis show that on resource-constrained devices, and especially when the device is ultra low power, the memory usage and memory transactions can become the main source of energy usage. The reason for this is that lots of data has to be fetched from the memory, and because there is not enough cache to store the data on chip, there cannot be any exploration of temporal locality. For that reason, the data has to be fetched always from the memory, used, and that's it. And the next time it has to be fetched again. And this process results in lots of inefficiency in terms of data transactions and data movement from the memory peripherals and the buses to the computation unit. We propose to apply clustering algorithms and specialized clustering techniques on the model parameters to reduce their memory size and consequently reducing the energy consumption. In this work, we are going to use k-means clustering algorithm as an efficient and non-linear quantization algorithm. The model parameters can be reduced by more than 4x with negligible impact on the overall accuracy. By using the k-means, the parameters of the original model will be grouped into multiple clusters, and then the original data will be transformed into a set of indices which are referring to a table of centroids, and the centroids will be representing the original data. In this work, we are also proposing two ways of clustering. The first approach is to cluster the entire set of parameters all together. Then we will have all the data clustered with a one single table of centroids. The second approach is to use a per layer clustering approach, meaning that every single layer and its data will be clustered separately and they will have their own table of centroids. The benefit with the per layer clustering approach is that smaller data sets will have the same number of table of centroids, and overall we can have much more number of clusters, resulting in providing much higher accuracy. Now we are looking at the clustering from implementation point of view. In the baseline models, we have the model parameters as 32-bit floating point values, and they are usually stored sequentially in order to exploit special locality. Then by applying the clustering, instead of having 32-bit floating point values, after the data is being clustered, indices will represent the original values. Being said that having around 256 or less number of clusters, we only need 8-bit indices to represent 256 maximum number of clusters. Therefore, by applying the clustering, instead of the original 32-bit floating point values, we just store 8-bit indices or less number of indices if we can get to use less number of bits. So the benefit of reducing the memory size of the model and also less number of data transactions coming from the fact that for every single parameter now, instead of 32 bits, we are using 8-bit. After fetching the indices, when we are using the clustering, we have to do a fetch of the corresponding centroid from the table of centroids and then provide this as the representative value for the original parameter. Then this representative 32-bit centroid will be used instead of the original value. So that is the main difference from implementation point of view when we do clustering. After introducing our approach and the implementation perspective, we are now presenting the methodology, the platform setup and datasets first. For the evaluation, we are considering three different architectures and hardware setup. The first is having a high-end desktop CPU and GPU. By CPU, we are using the latest i9 processor and an NVIDIA 2080 Ti GPU. The second configuration is the embedded NVIDIA Jetson TX2 platform, and the third configuration is the NVIDIA AGX Xavier platform. For datasets and running the inference on both of the DEIT and VIT models, we are using ImageNet validation datasets. We also evaluate our approach by considering 4 different metrics. The first is the observed speed up in terms of frame per second. The second is the accuracy by means of top 1 and top 5. The third metric that we use is the memory usage by comparing the baseline model memory usage compared to the clustered model memory usage. And the last metric is the energy usage of the overall system. Now we start to present our results. First, we focus on the accuracy results. As you see, when we are using different number of clusters for the DIT model, the graph in the left side of the slide, we have 4 different number of clusters from 16 to 128. The more the number of clusters, the better the accuracy. As you see, for 128 and for 64 clusters, the accuracy that we got is almost identical to the baseline, meaning that if the model is represented by only 64 or 128 number of clusters, we can get almost the same accuracy as in the baseline. However, by reducing the number of clusters and simply reducing less number of bits for the indices, the accuracy starts to drop. Here the difference is that when using the per layer clustering, when we have less number of clusters, the approach of per layer clustering provides much higher accuracy compared to when we are clustering all the parameters together. That's why we see that the yellow line is providing much higher accuracy compared to the blue, which is when we cluster the entire parameters. We observe very similar behavior when with the VIT model. We observe that when we are using 128, 64 clusters, the accuracy is almost identical. Even when we are using clustering of the entire parameters, but when the number of clusters are reduced to 32 and 16, we observe that the per layer clustering still provides much higher accuracy. Now moving on to the results in terms of performance improvements, speed ups, and also energy savings, we observe that across different configurations we observe some speed up, which is the highest in the third configuration, and after that in the second configuration, which is the NVIDIA TX2. And regarding the energy consumption, the highest benefit goes to the desktop configuration, and the main benefit comes from the fact that all the transactions from the memory to the device and also the storage of the data is significantly reduced when we are doing the clustering. We also did a memory usage breakdown, and as you see that in the analysis of the memory usage breakdown for the VIT and DIT models, in the layers that they perform the matrix multiplication, like the convolution and the linear layers, we are still considering 50% of the whole parameters which are consuming the memory. Finally, to conclude this presentation and the work that has been done, we have provided analysis of state-of-the-art vision transformers in terms of execution time breakdown, memory usage breakdown, and the accuracy. We used and proposed clustering approaches in order to provide significant performance and energy improvements with negligible impact on the accuracy. We showed that when using enough clusters, we can achieve the same accuracy as in the baseline with only 64 or in some cases 128 number of clusters, and this can significantly reduce the memory usage and the memory transactions. We presented 2 different approaches of clustering in order to model the parameters and also the trade-offs that we observed. We showed that the potential performance improvements can be very high on a variety of hardware platforms. We also saw that higher performance is achievable by employing specialized hardware accelerators and designing hardware-specific design for benefiting the most from the clustering of the data. Thank you very much for your time.